Let's get started, okay? Ladies and gentlemen, so welcome to the Forum of the Great Minds. It is my great honor, on behalf of USTC and personally, to thank all of you for joining us today. In 2016, USTC launched the Forum of Great Minds initiative. Each year, we invite about 10 world-renowned scientists who remain active at the forefront of the research to visit USTC. Through this initiative, we aim to bring students closer to the global frontiers of science and technology. By listening to the life experiences and academic journeys of these great minds, students are inspired to bridge the gap between theoretical knowledge and practical application. Okay. It is my great pleasure to introduce Professor Piero Baglioni. He currently serves as the chair professor of physical chemistry at the University of Florence, director of the Center for Colloid and Interface Science in Italy, and is a member of Academia Europaea. Professor Baglioni is a globally recognized pioneer in the field of nanotechnology for cultural heritage. He has long been dedicated to the interdisciplinary research of colloidal science, soft matter, and heritage conservation. His groundbreaking work includes the developments of innovative materials such as calcium hydroxide nanoparticles, microemulsions, and twin-chain smart hydrogels. Notably, the Nanorestore series, developed under his leadership, has been widely adopted in conservation practice worldwide. His impact on the scientific community is massive. He has published over 600 papers with an impressive H index of 84 and more than 30,000 citations. It will go up and with time too. He has also led major EU projects like Nanorestore and GREENART, earning up his top honors, some like Overbeek gold medal and etc. So, as a token of our appreciation for his time and valuable insight, we would like to present a memento to our guest speaker, Professor Piero Baglioni. Let's welcome Professor Wang Chen, Deputy Director of the Office of International Cooperation, to present the award. Come on. Yeah.
Okay, while I'm disconnecting, okay, this is, then I need the, no, this one. Ah, okay. Yeah. So.
I'll do the sentence.
You had something else? Okay, you go ahead. Oh,
It's working?
I don't know. It's
Okay.
okay. That doesn't matter. It's no, it's okay. It doesn't matter.
Yeah.
It should work. Okay, go ahead.
Okay. Today, Professor Piero Baglioni will give a lecture entitled Colloids and Surface Chemistry for Art Conservation, sharing his scientific career in heritage conservation and surface science. Ladies and gentlemen, please give a warm welcome to Professor Baglioni.
So, okay. So really thank you for inviting me and for this, say, magnificent introduction. So, okay, so I was asked to give a lecture by that last 2 hours. So maybe after 1 hour and a half you're tired. If you're tired, just let me know that I can make it shorter because it depends on you. So thanks again for the invitation. And then I'm trying to give you an overview of what we have done and many other people have done during the year. So most of the most of the works we have done with many institutions worldwide, but could be done due to this center that we have in Italy, which is a center for colloids and interfaces. And this is actually a sort of consortium among many universities that works in colloid science and in physical chemistry mainly. What we do is nanotech, soft matter, and part of the activities dedicated to conservation of cultural heritage. And we work in a certain way that actually we have fundamental and applied research. We have training of students, so students are welcome to stay within the consortium. And we have industrial collaboration and also we have external funding that mainly are from European Union. So most of our budget doesn't come from the Ministry of Research, doesn't come from public funding, but comes from industrial collaboration and European Union funds. So the headquarters is in Florence, and in Florence we have many activities that are related to soft matter, nanoparticles functionalizing for different applications, mainly in medicine, in cosmetics, in detergency, and some activity that is in conservation of cultural heritage. And I will show you something in this field, so in this part. So now, this is, okay, so what is the way we can compare heritage to medicine? This is just to make clear what we are doing. So we have two objects. One is the artifacts in conservation of cultural heritage, and the other that are analogous to patient, and conservators that are the doctor. So what we do is basically the diagnosis, this part. We do mainly treatment and prevention. So we develop methodology that in medicine actually are related to prevention and treatment. So in medicine, when you have prevention and treatment, you need a doctor. And in our case, the doctor, it doesn't work. The doctor is a conservator. So conservator is the person that we are related during this activity. Most of the therapy that we develop have been developed by using different methodology from classical methodology, and because we use a different framework from what they've been is used by classic methodology. So how we start be involved in this activity? This is just at the beginning for fun, then it became a job. This is the fun was not at that time. So this is Florence, and at that time Florence, I was a child. At that time Florence was flooded by this river, and basically 90%, 95% of the city, downtown city, so the center was flooded. And Florence is a huge container of modern, classic and ancient art. So it's estimated that is about 15–20% of the world cultural heritage in Florence. Now it decreased because China discovered continuously new stuff, so we go down, and you go up. So, but that's normal. I mean, so during the Florence flood, what happened is this: that we had to develop. I mean, until Florence flood, there was no interest for scientists in the conservation field. But then during Florence flood and after Florence flood, they realized actually that there was many materials that were degrading very, very fast in a very fast pace. So they had to find something. And then at that time that there was people that started working and trying to find methodology and materials for conservation works of art in order to transfer to future generation. So beside these aspects, now what we can say is that, for example, in Europe, there's another point of view. Heritage is a good business. It's a good business because it has a revenue. It's about 335 billion euro in 2022 and generate more than 10 million jobs. And just to give you an idea, just last year, for example, just in auction and fair, they were traded about 60 billion euro in art. So art is also a good business. But the problem is that art, and in particular modern and contemporary art, because the difference is that say, classic art is made by very good materials, related materials, and they're not polymaterials. In modern and contemporary art, usually the artists use a polymateric, and polymaterials to realize their works. So it's very critical, the conservation. This is a clear example. For example, this is Jackson Pollock, which is the dripping, use the drip technique, and you see this, is painting in this way. So you have several bottles, different colors, different pigments, just spray on the canvas, and sometimes the canvas is not the canvas. Is a complex field. So it's very complex to keep and transfer to future generation. And then, so this modern and contemporary art degrade a very high, fast pace. And then if you look, for example, some museum, you see that MoMA is in New York. They have more than 200,000 works of art. And so Pompidou is more than 100,000. I mean, there's some museums, Rice Museum is 30,000 and so on. So you can easily understand that to keep 200,000 works of art, you need, I mean, it's not easy. So you need a particular approach to the conservation that cannot be done with the conventional, say, conservation, traditional conservation. So what is our approach? Works of art degrades, and where they degrade? All the works of art degrade at the interface. So it's the surface that is the main and primary locus for degradation. And so if you want to keep works of art, you have to choose the right scientific tool. And the right scientific tool is colloid and surface science, because colloid and surface science, they possess all the knowledge and is the right, say, framework to remediate the damage and the degradation of the surfaces of the works of art. So how could possible to achieve this new methodology? This is due to EU initiative in materials for conservation, and actually we were working in nano materials for conservation, and these nanomaterials can be applied to different, field of science and different activity. So they actually funded many projects like Nanorestart, Nano for Art, and so on. And the last one was GREENART. And so they put about 105 million euro, which is, considering the scale of China is a little money, but considering the scale of Europe and the particular field in conservation, it's lots of money. And due to this support, actually, we generate many innovation in conservation, and we have now families of products that can be, these are on the market, so you can get that are, for example, Nanorestore cleaning means that you have a methodology for cleaning, and I give you some example. Or you have some to absorb, so purify the air or the environment around works of art, or even in this room, by using organic absorber. Then you can have gel that helps a lot, and in two main family, that's hydrogel or organogel, and this gel helps a lot in the cleaning and increase and the cleaning capacity of solution that we use for cleaning, or something else that we use for paper conservation or consolidation. So, and you have some people here that is good in consolidation of artifacts like him, actually. So it's yesterday I've seen ivory conservation, so it was quite interesting and nice and important. So this is a flow diagram that you can find on the web if you're interested in using this, and then they tells you which one among the different solutions we propose you can take, and then you can get, for example, from this spin-off of the university where you can buy these materials. So just to give you an idea how it works, a European project focused on this is this. For example, this is GREENART. GREENART is a project that involved 30 different partners, and roughly you have a worldwide distribution. So we had people from China, from Chengdu Sichuan University, two industry from Japan, most of Europe, and then 3 centers in Brazil and 4 centers from United States. So this is a geographical distribution. We are writing a new project, and for example, I invited you to be part of the new project. And that will be, if we are successful, will be a nice opportunity. So during time, what we produce? We produce cleaning systems, protective coatings, consolidants, packaging materials, and solution for monitoring CH assets. And this can be used in many different activities, not only for conservation. And with GREENART, what we produce is solutions that are based on safe solvent, polymers, monomers, surfactants, and all the conservation methodology we develop are clean, sustainable, and safe for conservators and for the works of art. And in Europe, we have this this approach for green chemistry, which is called Safe and Sustainable by Design Framework. And this is 5 steps that are quite important. So the first 3 steps involve the health, so is the hazard by using chemicals or materials. So we study how some materials can be dangerous or can be problematic. Then we see if they interact with or affect the human health and safety in many aspects. Then we check for the environment, not only human, but also the rest of the environment. And then there comes the economic part, which is the environmental sustainability assessment, the social economic sustainability assessment. So if you have to pass step 1, 2, 3, 4, and 5 before putting on the market a new products. Just to give you an example. So for example, some solution is this. So just this, for example, this is the solution environmental footprint. This is the benchmark, and this is the solution we developed. So you see this higher is this bar, worse from life cycle assessment is the methodology. This is the mainstream, for example, for CO2 emission, and this is the solution. So you see there's a strong improvement. Now they're even better improved. So this I can keep. Okay, so let's check, and I will tell you some methodology. There will be many pictures because we are working on art. And if you're interested in the concept, if you're interested in the physics and the chemistry, then we can discuss physics and chemistry later, maybe, because I don't know the auditorium, so sometimes can be difficult. So the first methodology is called Ferroni-Dini method. And Ferroni-Dini method, there's evolution of Ferroni-Dini method is the calcium hydroxide nanoparticle. But calcium, not only calcium, we have magnesium, strontium, barium, zinc, and many other particles that can be used in conservation, but not only in conservation. We use in textile, we use in different activity. And this nanoparticle can be also used for paper and canvas conservation. So what happened to a wall paintings? If you have a painting on a wall, or if you have any monument, degradation comes from salt. So salt go in the porous structure of the fresco or the monument, and then by cycle of crystallization, liquefaction, what you have increase in the pore, and then the collapse of the say the matrix. So why this occurs? It depends on the solubility product that these compounds have. It depends on, for example, what you get during the degradation. For example, if you take calcite, which is calcium carbonate, which is the constituent, the main constituent of wall painting, this can degrade into calcium sulfate selenite. And what you see is this, that the unit, the molar volume change a lot, is about twice. So when you have the formation of sulfate, you have the complete decohesion of the pictorial layer. And Ferroni, what did at that time? He found a way to reform the calcium carbonate, avoid the calcium sulfate, and then to reform the original binder that the painter produced. So these are the two guys that work on the project, and these are the two unit cells of calcium carbonate and calcium sulfate. And you see one is about twice, it's more than twice than the other one. And this Dini was a restorer and Ferroni was a physical chemist. This is a simple reaction, 18th century chemistry, but it was very clever reaction. And then what happened is this: when you apply it, you start from this point to this one. So you see, this is just is a very fast reaction, 1 second. In 1 second, you have the painting. In this case, is a fresco of Beato Angelico, who is one of the most important Renaissance painters in Europe, is reverted to the original condition. So this is another one. This is Piero della Francesca. So this is before and after conservation. From left to right, it's 1 second, maybe less. So it's a pretty fast reaction, and you invert completely the degradation of the pictorial layer. This is another example. Here you see clearly. So you see this little bubble that you see on the surface is the calcium sulfate that has increased in the volume. So since increased the volume, it cannot go inside the wall. It has to come out from the wall, and that's what happened. And this is after you re-invert the reaction and you put back to the say carbonate state. And this is another example. This is another example, and so on. This is another example. This is a different calcium sulfate, because this guy Sogliani was not a very good painter, so he used a different preparation for the substrate where you had to paint. So he was quite porous. So the pores here are quite large, and the calcium sulfate grow inside the pore. So you see this white layer that you can revert, and you see back the original. Okay, this is we saw. So this method is complex. The method of Ferroni is very simple from chemical point of view, but very difficult for the application. So we decide to move in these nanoparticles, and then we move to nanoparticles. In this nanoparticle, there's many different strategy that we use. We start in 1989, where the particle we used were microparticle, and then we developed several different methodology for synthesize particle different sizes. So we can go from 2 nanometer up microns. So that's no problem. We just choose the right size we need, and then we develop. And then we have we have more than 18 different systems that we can use depending on the application we want to use. This particle can be used for paintings, but can be used also for paper. And paper is quite important, and I'll show you later. So lime, it seems simple, but it's not simple, because lime, it's a quite simple materials, but quite complex materials. Why? Because limes age. So it change aspects, it change properties during time. If it's kept in the solvent, and now in this case is water. So you see here, for example, you start from these properties, this point, and then after 400 days, a year, you have something that is about 10 times during the age. So it changed the property. It changed MLE plasticity, it changed the water retention, it changed the water content, and so on. So it's difficult to it's easy, but it's also difficult to work with mainly on the sides and side distribution. So usually we use particles in non-aqueous media, and then can be of different concentration depending on the activity that we want to use for. So these particles are like that. We can produce particles like rhomboedric particle or platelet, like this hexagonal prism or platelet, and between the two we prefer this one. And this platelet, this hexagonal platelet prism should be disconnected each other, so they should not interact each other. And this is not simple, but you can play with solvent like this. So you can play, if you play with the hydrogen bonding, say, of the solvent, changing the hydrogen bonding capacity of the solvent, you can start from aggregated platelet until dispersed platelet. So it depends on the application, but usually we want to be dispersed. So this, for example, is a neutron and synchrotron radiation experiment where we move from this case or aggregated case to simple dispersed particle. And you can easily follow by using neutron or the synchrotron. You have a synchrotron here is more than enough to do this activity in this kind of activity. So, okay, so the synthetic path can be bottom up, can be top down, can be that's 3 or 4 different methodologies you can use. And then you can get Portlandite with some, for example, this is 80 nanometer, but you can go also to 200, you can go to micron size and so on. And what is interesting is that you get a different, the substance is still the same, Portlandite, but the formation of calcite, that is the object that you want, it depends on many parameters like room humidity, depends on temperature and so on. So in some cases you have calcite, for example, but you don't have the other phase typical from the formation of calcium carbonate that cannot be it's not only calcite, can be vaterite or aragonite. And depending on what you get, it changes completely the properties. So where we use this, the first particle have been used here. This is Florence, and inside this cathedral there's paintings we use there, and since they have been used everywhere. And this application is pretty simple. So this is a layer, a pigment layer that you want to reattach, for example, on the wall. You take a brush and then, or you spray this particle, and then what happens is something like that, and you reattach, and you have a new setting process. You have this book we wrote 10 years ago, I guess, where is reported most of this way you should follow to achieve this. So this is an example. These are disconnected in a fresco. The pigment is green in this case, you see here, and these are the grain that are disconnected. You see there's no binder here, and then when you apply the nanoparticle, you reform the binder between the grain. So this is an example of the application is in Florence, and you see that there's here you see here that is reattached. So you see the difference from this and this part, or this and this part. So you see that this reattached. This is an example. For example, this in the jungle in Mexico is in Calakmul. They discover in a pyramid paintings, and then we went there to stabilize the painting. Otherwise, they cannot excavate the pyramid, because due to the difference in climate change, you usually lose the painting. This is an example of the pyramid, inside the pyramid, already treated. And this is the archaeologist in charge of this. This is an example on how simple it is to use this particle. For example, this is Decoy's painting, and we treat this an example we took in this area. So the pigments are mostly detached, and then you take a piece of paper, then you brush the nanoparticle, and then the nanoparticle is the painting. Here you see the layer is reattached, and here is almost detached. So you can put back on the wall if what is still there. If there's no there, you cannot do too much. This particle can be used for paper conservation, because most of the degradation of paper depends on pH and depends on two different methods, two different effects, that are hydrolysis or oxidation. And if you use particle, you can stabilize the pH around 7.5, which is the optimal pH for paper conservation. And you see this, what happened to the paper if it's not correct in a right way, is breaking. You have to, you throw away after a while. And this is an example that tells you how particle can be useful. So this is it's a simple example. This is a disc inked with a particular ink containing iron and copper, which is very aggressive to the paper. And then there's one disc that was inked but not protected, and another disc that was inked but also protected by nanoparticles. So we add some nanoparticle on the paper. And you see, after aging, this is completely broken. You cannot use this. It's very completely destroyed, and this is almost new. So there's the adhesified sample actually is in good condition, because we avoid completely the phantom reaction that destroy, in this case, the cellulosic fibers. So when you use particle, you also recover mechanical properties of paper. Some protection we gave this Florentine Codex is the most important book in Mesoamerican civilization that is protected by using nanoparticle. And the same nanoparticle you can use to keep paintings. For example, most of oil paintings are on canvas. So canvas is a fiber similar to paper, so it's cellulosic fibers, can be linen, can be other tissue, but they're the same. So, and then they are affected from the same effect, so they can be degraded. So if you don't want to degrade the fibers of a canvas, especially when the canvas is not in good condition, you have to deacidify and protect. Just to give you an idea, this is a short movie that show you how you can do this, which is this was a program from European Union, and this is one of the canvas of the Medicis family. The Medicis family had many villas, so they asked to this painter, this was Utens, to paint all the villa belonging to the family, and this is one of the villa of the family, Medicis family. It's a beautiful villa. And these are the nanoparticles. So this bottle is contain nanoparticle, and it's easy. So you can analyze, but you can also don't analyze because there's no reason. I mean, there's reason. It's better if you analyze and you check how much acidic is the canvas. But then, even if you spray more than the necessary, doesn't change too much, because this particle then are hydroxide, but then soon after spraying they become carbonate, and carbonate is a quite good protector for canvas and for paper. So this is the methodology. You just spray these things, and you will see that there's nanoparticles on top of the fibers, and then this is the conservation treatment. So these paintings don't need to be relined. So the canvas is not necessary to reline the canvas and glue back on a new one. And this is quite well protected, and it's been also recovered. We recovered also some mechanical properties. The same is for documents, for journal, newspaper, for these Chinese documents from Chinese students that was one of our PhD students we had. So he brought this, and then we can protect also that. And then what we can do, we can produce particles in different solvent. According to the polarity of solvent, you have different effect on paper. But if you choose the right solvent, you can do something that you cannot do in any other way. For example, if you want to protect something that is a 3D, which is quite common in modern art, this is a painting, is a Brazilian artist. If you want to deacidify, it's almost impossible with any other methodology, because usually you lose these 3D textures. And with this nanoparticle, you can do this. Is an example. So this is reflectance transformation imaging, specular enhancement. And here you see before and after. So you see the 3D structure, say textures of the painting. This is a Picasso Arienti. And you see that you didn't change the 3D structure of this. Here you can see much better. So you see that before and after are exactly the same. You can use, you can have particles that are produced not only by calcium carbonate, but for example, the Shofu, that is something that you might use, but for example, Japanese use a lot. I don't know if Chinese use or not, but it is something. And we made nanoparticles of this. This is traditionally used in conservation since 300 after Christ. So it forms high flexible and is highly adhesive film. And then actually we produced this because we had to protect from the Norwegian people for the Oslo Museum, the Munch collection, that is the painting by Munch where they have a defect, they don't have a binder, or they have a very, very poor amount of binders. So you have to treat with Shofu to increase the binding of the pigment, otherwise you lose the pigment. So this is the original, and then the other one, you see, this is if you don't treat with the ginsophum nanoparticle, you lose lots. The spots here means that it's materials that has been removed from the original. And here you see is white because you don't remove anything. So if you use dispersion, a different kind of dispersion, basically you keep 99.91% of the pigment that are on the painting. So silk, you can do reinforcement, for example, for silk using sericin and fibroin. So these are protein. Then you can change the random coil. You can increase or decrease the random coil aspects of this. And then using this, you can protect and strengthen the silk artifact. For example, in this case, you increase from, okay, here you regain almost the original before. This is the degradation. So this is the original level. And then you see that when you use, for example, this elongation means that you improve the mechanical properties because it's about twice of the pristine silk. So when you treat, basically you generate a silk which is better than the original, but if the silk is degraded, aged silk like this, and this is the pristine silk, you see that you can reach almost during the treatment almost the same level. It's a little, just a little lower than the pristine silk, but much better than the aged silk. And protecting silk, it's quite complex. So how long? You have to tell me how much because I have, okay, many things to say. This is a consolidation. Maybe you can be interested in consolidation. So this is an example of consolidation using nanoparticle in the right way. So this is the Statale University in Milan that is in Pietra, so is Angera stone, and the Angera stone degrades pretty well, is a particular stone, and is a dolomite, so it contains calcium and magnesium. So you have about 20-25% of magnesium. So you can produce particle that is a mixture of calcium and magnesium to reproduce exactly the same composition of the stone. And then you use this particle, and here you see how we can treat the stone. These are the particles. You just, we use particles that actually, there were about 3 nanometers for these stones. And you just drop the dispersion on top of the stone. So you have to use 2 different populations. One that is small to consolidate the inside, and one that is larger to consolidate the outside. And this is a tedious work because you have to repeat 2 or 3 times, 4 times the same treatment. But this is what you need to do if you want to penetrate deeper inside the stone. And now this is pretty stable. The same particle or similar particle can be used for consolidation of earth and masonry, but this is a different approach because this is a very important part of our buildings. Say 50% of the building in this planet are made by earth and masonry, so not baked. I mean, these are not fired. So, and they are quite unstable. So this is an example of adobe in Mexico. It's quite popular in Mexico. So this is break, and we decide to try to consolidate by using something that is related to cement. Cement has a phase that is. This is cement. Cement is actually a mixture of 5 components. So these are the 5 components that are called symbolically called like C3S, C2S, C3A, C4AF, and CSH2. So these are the components. And then when you mix, these are mixed in different amount. And then when you add water, you have the setting process. So you form hydrogen bonding and you generate new phases. So you can use these or part of these reactions to consolidate the unfired masonry like before. So which one? So the reaction that we choose is the first one. That is even the simplest one. So the reaction is this one, and it's called CSH. So you have to form calcium silicate hydrate. And how can you do this? Okay, for us it was quite simple. You take calcium hydroxide nanoparticle, silica nanoparticle, and then you form, by reaction among the two, you form these compounds. That is a CSH. And CSH is a poor binder of cement, but is a strong binder for unfired mansard. So this is due to a particular physics that the cement has, and basically CSH is a particular microstructural model where you form the CSH, and the CSH forms in two, say, different cluster condition. There's a low density cluster and high density cluster. So you had to form, if you want to have consolidation, you have to form first the low density cluster and then let them age up to high density cluster. And this is the problem. Okay, so this problem we could solve, and then okay, this is too complicated. And then we solve in this way. You can use nanosilica. Actually, you can get from this company, but even many other companies. So you should have nanosilica with a very large surface area. Calcium hydroxide nanoparticle, you can choose different sides, but then if you choose different sides of the particle, you change the final products. Can be stronger or less strong. And then in this case, we use hydroxypropyl cellulose because you have to subministrate water in a certain kinetics. So you cannot give the water all together because otherwise the reaction cannot occur. And then when you do this, you see that you improve for example, the mechanical properties of the weight loss from, say, this is 4.4 to 0.74. So you decrease by a factor of 5, more than 5, 6. So which is a lot. It means that you increase the resistance, the strength, you strengthen consistently the product. And moreover, you don't change the color. So these are the fine products that you compare with this one. So the color is about the same. So this is for consolidation, for the works we did with particles. But most of the last activity we had is on cleaning. And cleaning is interesting because it's fun. It's real fun because you remove something from, say, important painting, important artifacts. So it's at least for me, it's fun. So cleaning means this. So you start from something that is looks not very well, and then you get something that looks well. So this is an example of cleaning. So this is an area uncleaned. This is cleaned, and this is uncleaned. So here the snow is white, here the snow is yellow. Or this cleaning. This is, for example, Leonardo da Vinci. So this is uncleaned, and this here you see two heads. So and here you don't see the heads, or here you don't see people. So this is a very important paintings from Leonardo da Vinci, and this is partly clean. So clean. It's better than unclean. You can see easily. So cleaning, what means cleaning? Cleaning means removing something. So this can be common soiling and dirt, aged materials, detrimental materials, or you have to solve something that was subjected to fire, for example, or floods, or microorganism, biological contamination, and so on. So we know three main methodology for cleaning. One, this classical chemistry. So you use pure solvent or their mixtures. And this is something that if we can avoid, we avoid, because this is not a very efficient way for cleaning something. Then we can use some more, say, modern solution like using surfactant or microemulsion. And then the most advanced is to use gels that confine this cleaning solution, and you have a full control on what you actually wants to do. So this is okay, why traditional cleaning methodology are poor? I mean, it's better if you don't use. Because traditional cleaning methodology, you use a non-confined, mostly organic solvent. So you have system that you cannot control where the solvent is going. And moreover, it's toxic because it's an organic solvent. So you cannot control. The solvent can migrate, can go to the stratigraphy or the artifacts, and then you have solubilization, leaching, and so you have many, say, drawback in what you do. So solvent and solubility. What you do when you solubilize something, you use the Hildebrand approach. So you check the energy of interaction between the solvent and the materials that you want to solubilize. And this is quite approximate, say, methodology. So the Hildebrand was developed further by Thies, and then Thies produced this sort of diagram, and this sort of diagram are called Thies diagram. In the afternoon, she asked me about this diagram. So where you have these spots, and this means that this is the forces due to the hydrogen bond formation. This is then you have force of van der Waals and polar forces. So depending on the amount of these three parameters, for example, alcohol are in this area. If you have a materials that is in the same area of the alcohols, means that the alcohols can solubilize these materials. So usually in conservation, what you do, you want to solubilize paraloid, which is this molecule, and then you check which solvent. This is the the diagram for paraloid. So in this area, which are the solvents that are in this area? So you can use this solvent, this solvent, this solvent, and so on to solubilize paraloid without any control. So what we do? So we do something different. Can we use a different approach? And then basically we can do it. We can do this. It's quite simple because you use the same idea. So why you have a dirty layer over your artifacts and you want to remove the dirty layer is due to the process that is called adhesion. Okay, so the adhesion is governed by this law that is S coefficient that is called spreading coefficient. So if I know these parameters, that's quite mostly common and mostly easy to measure, I can understand better, I can understand what is the force of adhesion of this layer that you don't want over this one. So if you want, I want to clean, I don't need to solubilize. I need simply to remove this from this, just forcing, giving to the system the energy necessary to get the reverse process. So this is a cleaning. Cleaning means you go in the other direction. And how can you go in the other direction? You have to change the spreading coefficient. And how can you do this? Well, it's easy. You can do by using, for example, detergency. And detergency, you can use the detergency process that is part solubilization, but part also is another process that is called de-wetting. So depending on the material you want to remove, you have different mechanisms for low molecular weight substances, high molecular weight for polymers, and so on. So if you look at this and these materials, actually, you find a methodology to improve the cleaning. So this is what we do. So this is what is this? This is the layer that is on top of the works of art. So how can we remove? So we have to force this layer to be removed from the surface, and you go this direction. When you go this direction means that you have to change the interaction energy between this layer and the other. So this is the optimal physical, say, condition. So this is a lotus leaf. So if you go outside here, you have this process that is quite common. You can see you put a drop of water and that's all. So how can you do that? Well, you change this angle, and you can change this angle by changing these parameters that are called surface tension. And this is something that is common, and there's many substances that can do this. So you have to go from spreading process and a non-wetting process. Sometimes you can do non-wetting, sometimes you have to reverse partly the spreading process. So depending on this S parameter we saw, we can have total wetting, partial wetting, or non-wetting. So this is something that we can do. And how we know how to do. We use this system, micelle, microemulsion, and then in gel, with gel, you can do something even better. So microemulsion is systems complex, say, but not too much. It's just oil droplets that is stabilized in a continuous phase of water by a surfactant. So something that is the interface between the oil and the water. And this we use a lot. So when you formulate this kind of objects that are from 5 to 150 nanometer, basically what you do, you see that you can say formulate one microemulsion, and one microemulsion is one of the most popular is this one that is formed by several different solvents, like PC is propylene carbonate, xylene, ethyl acetate, and pentanol. And what you see here, you see that there's some propylene carbonate, for example, is well outside the diagram, the TIS diagram. So this means that this is not a good solvent. It should not do anything. This is not a good solvent. It should not do anything to paraloid. But then cooperatively, this acts in a way that you increase a lot the capacity of cleaning. And this is the best system for cleaning the works of art. This is cleaning by solubilization, but you don't want to clean by solubilization. You prefer the wetting. So the wetting is this. This green layer is a polymer. Actually, it's paraloid. Can you remove paraloid? Well, paraloid can remove itself. So you don't need to work. Paraloid is working for you. For example, okay, this is you see that if you increase just temperature, a little temperature, the paraloid detach from the substrate and separate in small objects. Then you do like that, and this object get out from the wall. But this effect depends on many things. Depends on the solvent, depends on surfactants, depends on molecular weight, depends on something. So you have to study in the right way this right system to remove what you need to remove. This is an example. So this is actually classic solubilization chemistry. So here the system is this one. Actually, well, it's difficult here. So the system is this one. So it's a glass slide. This is paraloid, and this is the microemulsion. So when you see red, you look from the bottom in top. So when you look red, it means that you have this paraloid layer. If you start seeing whole, means that the microemulsion starts solubilizing the paraloid. So that's why you see the color. So if we do this, you see that this is real time. In real time, you see that the microemulsion is solubilizing part of the paraloid. So you have to redo this process several times, and then you don't clean in a very good way, because to have this glass fully clean, it takes a long time. Now, suppose you use another part of physics, or in this case is physics, and you use a different approach. Okay, the different approach actually is the other approach. So this is the wetting. Well, you see here that is interesting, because in this case, what you see is that you can, so the surface clean itself. So you see that it start cleaning, and that's perfectly cleaned. So you want this way or the other way. You want that way. And this is the way we use and we are using. We are using that way for what? For cleaning artifacts, and these some artifacts, like, for example, this one. So this is one is Masaccio in Cappella Brancacci in Florence. This contamination is wax, and this is classic cleaning methodology. You see that this is a UV light, and this fluorescence are due to organic material that is inside, that penetrate during solubilization with the solvent, penetrate inside the wall. So it's because the wall is porous. So you see here, and this here you see cleaned by using microemulsion, because it doesn't penetrate inside the wall. It acts in different way. And this is actually before, again, and after cleaning, and so on. This is the full cleaned, say, panel. Then this is another one. This is Tiziano. So you see before, this is paraloid, age paraloid, and after cleaning. This is another this is a Nazareth Basilica. So this is important for Christians. So this is a place where it's supposed, the Virgin is supposed to be announced. So of her maternity. So, but this is some that these were treated, this wall painting or painting that lasted 17, no, is maybe 100 years after Christ. So they were in very poor condition, and they could the conservators could not remove this layer, polymer layer, by using any classic methodology, and this now is fully clean. This is another example of cleaning. So now we can use gel, and gel is a good system to confine liquids and to impose to liquids, say, a behavior that you want from them. So it's difficult to impose to a liquid a behavior, because the liquid usually goes where it wants. But if you confine in gels, and then actually if you study and you impose a diffusion coefficient that is the right diffusion coefficient for the cleaning, it's the most, say, important system and the most efficient system for cleaning. So the gels, why the gel? Because the gel are made in a particular way, and you can control fully the chemistry of the gel. This gel can be used for cleaning artifacts, but can be used also for cleaning skin or for delivery to skin. So they can be used in cosmetic, and in part I use some of them in cosmetics. Some of them you are using, you don't know, but you are using. So this is how can you use this gel? You can use it as they are or with something inside. Okay, this gel are not common gel, are particular gel that are so-called twin-chain polymer hydrogel. And these are the most efficient gel, and you see some cleanings. So they were originally formulated by Peppas, is a very important scientist in the United States, and then we modify in different way, and we invented the different class of gel. And gel can be based on this polyvinyl alcohol, which is a polymer, a toxic polymer, and very common polymers, or can be based on starch, and starch you know very well, I mean starch. So depending on what you want and the amount of release solvent you want to release, you can use different gels. So a gels is like that. So you have something with the 3D structure, they have channels, so it's like a sponge. And then when you want to clean, if you put something here, it has to go to reach the surface that you want to clean and then go back. So if you control the time necessary to reach this area and the time necessary to go out from that area, basically you control everything. And if you want to control this, you have to control a parameter that is this guy, that is called tortuosity. Usually this parameter is used in geology, but we use for this gel in a similar to geological effect. To change it, to control this, what you have to do, you have to make pore inside the gel. So you have to change the path, the length of the path, and doing this, you have to make a porogen strategy. And we use cryogelation for this porogeny say, activity. So here you see a gel, for example, this you see here, there's a channel. So this is an oriented gel, is not a spongy gel, is a vectorial gel. And this is, if you cut here, you see the hole. So you have vertical channel where you can use, I mean, this is very useful for capillary suction. So it depends on what you want to do. We don't want to have this because it's difficult to work with this, but we want to have something more disordered. And to disorder, we use what is in physics is a phase polymer-polymer phase separation. So we use something that is much more disordered, similar to a sponge. And then we can control the sponge, so we can control the pore, and the pore can be large pore or can be nanopore. So basically in our system we have two populations, which is our micropore, microporosity, or can be a nanoporosity. And if you want to study nanoporosity, again, you have to go to your synchrotron and do some experiment in the synchrotron. So this is something just to give an idea. Now, depending on how you formulate the gel, you see that you can change the tortuosity. This means the time necessary for something to remove something else, to interact with something else. And here you see the effect. If you tune the right diffusion coefficient, this is exactly the same stuff with different tortuosity, so different coefficient diffusion of the materials that is supposed to remove the dirty layer. And you see that this is not working too much here. It's better, and this is perfect. So here you see what has been removed. So we have a full control on what we want to do. And this, for example, can be the reverse, can be delivery. You want to do transdermal delivery, you use the same process in the reverse. And these are how look like, for example, the gel for the micro porosity. Okay? So now, what can we do with this gel? Because this is a sort of little theoretical, say, treatment. So you can clean. For example, this is cleaning from polymer, polyvinyl acetate. And these are the first experiment we did. So this is paper treated with polyvinyl acetate, PVC. And you see this the area that has been treated. And for example, this is another area. So you don't see too much from here, but now you will see better from here. This is a watercolor, and this watercolor was treated with paraloid. So it's very difficult to remove paraloid from a watercolor, and this is, you don't see too much here, but this area has been treated with the gel. And then here you see in a UV light, this is the clean one, and this is not yet clean. And this you see some cleaning. So here you see much better the cleaned area in regular light and UV light. Here you see again in UV light and regular light. This is UV. You clearly see that this is clean and this is clean, and this is the test. So these are different cleaning. For example, removal of pressure-sensitive tape, we call Scotch. And this is quite complex system because it's a multi-layer system. So it's usually, sometimes it's not easy to remove because most of the cases you break the paper. These are used to put together a piece of paper, and then when they are aged, it's difficult to be removed. So we can remove by using gel, and we can decide where we want to reach. So for example, this is the paper. Suppose this, in this case, is glass. And this is the pressure-sensitive tape. We can stop, depending. It's a multi-layered system, so we can decide which layer we want to remove. And actually is what we do. So for example, here, this is a fluid that in between, there's a tape. And then we see that we can penetrate below the tape by using this formulation, for example. This means that we can remove all the tape, but this is something that is here, you see here, there's the tape, and you can remove the tape in this way. You put the movie is not working. So this is an example of tape being removed. This is an application. This is Fellini. This is Fellini drawing. Is a very famous movie director. On this is Kit Haring, which is quite famous modern painter. Street art painter. This is other example of removing the gel. Here, for example, you see here has been not removed, still there, and this is the part that's been removed. This is something that you cannot do in a very easy way. So now you can use this also in regular paint, and then after some movie, I'm done, I'm finished. So this is an example of how a conservator clean. So this is a typical cleaning. This actually is a cleaning on Pollock that we clean in different way using our methodology. So you have to clean with cotton swab under microscope because you want to remove the layer, the dirty layer, this part, you want to remove this, but you don't want to solubilize the original. So you have to go point by point, and then it takes forever for the cleaning process. Now, this is traditional cleaning. Now, this is a different kind of cleaning. For example, this is an example where you can clean by using de-wetting. And this is a painting that cannot be cleaned with conventional methodology, because if you use a solvent or whatever you use, you remove the layer that you want to remove, but you remove also the original. So this is an example that is quite clear. And so this is something done in the United States. And she's using a gel on that painting. And this painting is a very important painting of the last century. So this is the gel, a piece of gel with a microemulsion. And then she takes the gel, and then first she tries to check what is the time necessary to remove the layer. So here we have two layers, the original and something that is in top. The gel is formulated in a way that contains materials, solvent, that are solvent neither for the original or for the layer that you want to remove. So you apply, and then you see that you're detaching the layer, the top layer, from the original by simple methodology. So this is quite simple and pretty fast. Now you will see better in the next. So she apply a better, larger foil, and now you see you remove the layer in very easy way. You can see here. And the solvent used are solvent that cannot affect the original or the layer that you want to remove. So this is the polymer layer that actually was not the polymer, that you can easily remove simply using a different properties, that is a de-wetting of the layer. So we basically send something at the interface between the original and the layer that you want to remove in order to decrease the attraction energy between the two. So the upper layer was not adherent anymore to the lower layer because there's no adhesion at all at that point. So this is something that you cannot do. This is another example that you cannot do with conventional methodology. So this is an example. So this is a water-sensitive oil paint. So this is a layer of dirty, so it's experimental layer, is a Tate layer. And then you see that if you want to remove this soil, basically at the end you have to use water because it's the only case you use, but you remove also the original. There's no way to remove the soil from top if you don't remove at least partly the original. But now if you use a gel, the water that you use to clean is fully confined into the gel. And then now you see what happens. Since the water is confined, I mean, the layer is detached, is clean, and the red, I mean, the pigment is not affected at all by the water because there's no water locally. It's just into the gel. So when you push in that way, you put some water and then it goes back into the gel. Now you can remove the layer and you see that the gel is clean. I mean, it's dirty because the soil has been removed, but it's clean. And then you can complete the cleaning by using a different shape for the gel, actually, like a rubber. I mean, so this, and you can push as much as you want. You cannot do anything to say the pigment. So this is another example. I can skip this because there's too many. These other paintings, for example, this is one for Roy Lichtenstein. This was in Tate Modern. This the paint after cleaning. This is something that could not be clean because the varnish, I mean the paint, the color he used are fully soluble, so in water, and then it's impossible to remove the soil from the surface of this painting. And this is another example. This is, for example, a cleaning of Jackson Pollock. So this is the gel. The gel is with the microemulsion. We went in the afternoon. These are the same system we use, I show in the afternoon in the museum. So this is the Pensabene from Peggy Guggenheim. So you put a piece of, this is water actually with TAC, trimethylammonium citrate. You just push the gel and then you remove in this case, and then under what you do when you do this, the lower part is clean. And since Jackson Pollock is quite rough painting, I mean, it's not even, you can complete the cleaning with this sort of pencil, I mean, rubber. So this is what happened after the cleaning. So this is before cleaning. This is 2 by Jackson Pollock. And this is the ice in the heat. So this is the clean part and this is the uncleaned part. And then this is another example. This is Picasso. Picasso is, this is Atelier. It was one of the favorite, I mean, panel from Picasso that Peggy Guggenheim took for her. And these are example of cleaning. So this is, in this case, the guy used a microemulsion because he wants to remove a wax that was used to during a reline on the back of the canvas, and then this wax with the temperature, with the time, it move on the surface. So this is an example. And then now you see, so he made the test, which is quite simple test, and because this is the first time he used microemulsion, so he was suspicious. He didn't trust too much. So is what he did actually. He make a test there, and then he removed the wax which is on the surface in a very simple. This is in real time actually. And then he removed using this way. Now he uses a different way, which is much better because there's no abrasion on the surface. So this is the Picasso. So this is before cleaning on the left. This is in black and white. You see the cleaned area, and this is after the cleaning. This is another one. This is Piet Mondrian. So this Piet Mondrian, they had to remove the varnish from the surface, and this is a test before and this after. So now is an exhibition, is fully clean. And what is nice is this, that you can, with the gel, you can really easily control the area that you want to clean. So in this case, it's very precise, the area. This is another example. For example, this is Modigliani on the left and on the right, which is clean. This is a street art. Street art is interesting because usually the vandalism of street art is made by using exactly the same composition used by the artist. Suppose you can call artists. Some are artists. So it's difficult to remove because you have acrylic layer over an acrylic paint, and then it's difficult to remove acrylic over acrylic. And then if you use gel, confined gel, you can do that, you can do easily. And this is an example. For example, you see here some test. This is a test of the area cleaned, or this is the test of the area cleaned. And this is another test. You see this is NO, and now is clean piece by piece. Or here is cleaned, this beginning, then partly clean, and this is cleaned, and so on. So an example is Banksy, because maybe you know Banksy, and why I don't understand. Okay, Banksy, and this was Banksy was vandalized. This is in after Katrina hurricane in New Orleans, and Banksy went to New Orleans and made several sketches like this. And then there was a guy that vandalized. Using the same red, he sprayed the acrylic over the Banksy painting. And then it's you can see here that if you use this method, you can remove a layer of acrylic from a layer of acrylic, because we actually control completely the cleaning process. So this is an example. So this is some music that you see that's applied the microemulsion with the gel, and then you can see that you can easily remove, and then if you want, you can wash out the pigment. And this is the recovered, say, area. Now it's finished, so it's back in exhibition. Now this Banksy is in a restaurant in the United States. Then the last one, I don't know, yesterday I had a dinner with the person that was working with bronzes. I don't know if he's here, but anyway, I added something on bronzes, and you can easily control, say, the cleaning of bronzes and the anti-corrosion, say, of bronzes. This is the bronze usually are affected by this autocatalytic reaction, and this reaction, once start, it never stop unless you take out part of the products, and then it continues until no remains. So you destroy completely the amount of copper that is in the bronze, and this you can clean easily by using a gel, and this gel is a pH sensitive gel, and playing with the pH you can play with the cleaning capacity. So here you see the extracting capacity. When you see the color blue, means that you have complexed the copper coming from the paratacamide, from the corrosion, say, salt. And then, so in this case, the optimal condition are, of course, these, you see the highest concentration. So this methodology has been used in Peggy Guggenheim, in this statue, bronze statue, but also can be used for coins. These are Roman coins, where you can control the cleaning in time. Say during, it depends. So is this is 6 hours or 12 hours of application of the gel. So you put the gel on the coin, and then you go after 10 hours. Or I mean, you can do like this. This is a very important, say, cleaning, because this is Benvenuto Cellini, and this is an important works of art from Renaissance. So this is before and after cleaning. You can use similar methodology also using not hydrogel, but also organogel. So I think I can stop here, because I guess it's enough, no? And this is organogel, and organogel is a new class of organogel. And if you use organogel, you use a methodology that is quite close to conventional methodology used by restorers. So we decide also to give the possibility to conservators to use something like this. This is more close to what they're used to do day after day. So you see, you just drop this organogel And here you see that the varnish has been removed. So from here to here is something like 3 seconds for the cleaning. So the acknowledgement. Well, this is something that we start doing for fun. And during the year, it increased the activity. So there's many people that work on this. It's simple. It seems simple, but it's not so simple. And there's this something that, works with art. There's these are most important scientists working in the field, but mainly there's more than 200 scientists, and we have 38 museums around the world and research center and university that work with us. You could not, say, realize materials like this. You could not formulate these systems if you don't use large-scale facility, and actually you have to use heavily neutron large-scale facility, neutron, and synchrotron radiation, because this system works because they works at the nanoscale. And if you want to understand what they are doing, you have to be at the nanoscale, and then you have to use these instruments to check what you have. Then what can I say? If you like art and if you like the field, well, there's plenty of room in conservation field, so you can try. Especially in China, you have to excavate a lot. So because you have lots of remain that you still don't know yet, but you will know in a while. So thank you anyway for inviting me, and I hope you're still alive after this talk. Okay, great. Thank you.
So that is an excellent talk, and thank you, Piero. And now we have time for questions. So I'm sure Professor Piero will be happy to answer them. Yeah.
Yeah, thank you. A very interesting and important topic on the art protecting. And I'm very interested about the green art technique. Green, especially green chemistry method to prepare materials, or what is the materials you choice based on the green art idea?
Okay. So basically, we start from classical materials, and then we search if there were some materials with similar properties but obtained in different way. So we have some that there's many labs that are working in replacing fossil materials or other solvents and so on with other solvent made and obtained in different way. So we reformulate all the old system using a different class of material coming from other, say, way of making this material. So that's why this SSBD methodology is quite important, because you have to screen each substance before using. Then if it's the screening, it's okay, you can start thinking on how to replace the old one. But you need this pre-screen, otherwise it's almost impossible. So we screen something like 2,000 or 3,000 different, for example, solvent. And from that, we extract 12 that could be used. And then we try to reformulate in different way the same similar system, actually, that are as good as possible compared to the original. But in some case, I tell you, the old chemistry is much better than the new chemistry. So it's something that you can, old chemistry, it's difficult to read out. So it's...
Okay, thank you. Another question. For your materials, especially for the gel, for the cleaning, the solvent is very important. Usually you use water or alcohol. I sometimes use organic solvent. But I think it is important to protect the art itself, not damaged by the solvent. When you shoot a movie, something have been directly to move from the edge layer to from the arch. Maybe they are dirt or something not such as pollution, but maybe it also the art itself. How to degrade them is dirt or the art itself.
Okay. Well, this it depends on works of art. Okay. So usually the system we develop, you can precisely say choose the level where you want to reach. For example, in Picasso it's pretty easy. It's not always easy. But in Picasso it's pretty easy because Picasso paintings, they have a fingerprints, and the fingerprints is a layer of oxalate. So the original is there's a monolayer of oxalate on the surface. So we formulate the system in order to reach the oxalate, but not to interact with the oxalate. So you can easily remove what is above the oxalate without touching the oxalate. So using gel and this system, you can do that. If you clean by hand, you remove also the oxalate and then you go down. So you don't know exactly where you go. So what usually conservators do is that they don't remove everything. So they leave on top of the surface a layer that you don't see very well because maybe the thickness is small, but they still keep a layer of the non-original same material. But we can be much more precise than that, and it's much more easy and fast. So and then the oxalates are quite useful because you can remove easily what is on top of the oxalate. So and each painting has a similar fingerprints. So we can easily detect the original from the non-original. But the conditions are quite simple. So the original surface should be a surface that has been aged before somebody, say, apply a varnish on top. So you need when the artist finished painting, if he just varnish the paintings the day after, we cannot detect the interface between the original because when they apply a varnish, they penetrate inside the original. So there's no real clear interface. But if the varnish is applied maybe 2-3 days later, the first layer, the original layer, is oxidized by oxygen, and then at that point you can really discriminate the original from not the original. But then if you want to do, you have to go in synchrotron or neutrons. I mean, you do reflectivity to see where is the layer, because it's a monomolecular layer actually, so it's not so easy. Welcome.
Any other questions?
Thank you. So one question related to what you were just saying. So in the case when you removed the acrylic applied over the acrylic by Bansky, so that's because in any case, even though the composition was similar, the adhesion between the second layer and the first one was lower than the cohesion within the first layer of acrylics.
Exactly.
Okay. And I also have another question related to the consolidation part. So you mentioned that, as I know, your products are based mostly on alcohols, so meaning dispersions of nanoparticles in alcohols. So I was wondering, because I know there are also products that are based on hydroalcoholic or sometimes even water-based dispersions, and I know they claim that it helps carbonation and so on, but I assume it also favors agglomeration. So I was wondering, what's your opinion about these other products?
Okay, if you have nanoparticle, if you want small nanoparticle, cannot be in aqueous solution. So people can get small particle if they add surfactant or other say, molecules that interact at the interface of the particle, so you avoid the growth of the particle. But then if you want to work in art, this means that these surfactants, you inject this surfactant in the works of art. And this is something that we don't want. If you can avoid, it's better to avoid. Moreover, if you work in water, you delay the carbonation. Because if you look at carbonation reaction, for example, if you are above 90% of relative humidity, you don't have a reaction of carbonation. So there's a range of relative humidity that you need to maximize and to optimize the carbonation reaction. And you must know what is the range and what are the conditions, because the consolidation depends on this. So if you work at the right humidity level and the right temperature, you have a very good consolidation. If you work in a wrong condition, you don't have consolidation. Same material, but completely different effect. That's why I say that is a simple but is very complex material, because there's many different possibilities.
Thanks.
Okay. Any questions? Maybe we get one from student.
They are tired.
Student want to ask a question?
Okay.
No? Okay. I might have a question like this regarding, it's not regarding to the research, but so when you want to apply the material, I mean, a lot of times you have to get a conservators involved. So how do you collaborate with those conservators? Some of them are skeptical, or some are like conservative. Like it's not that easy. Sometimes like they don't.
The first time they are always skeptical. The second time are still conservative. The third time maybe they start trusting you, and so they try and they check, and then we do together, in the sense that they know better how to apply than we do. But they don't know maybe the physics of the chemistry, so you have to explain in order they can apply in the right way. But usually they do what they want, and each conservator apply these materials in a different way. I'm amazing they are working, because it's a different methodology. But this is, this is the case. So you have good conservator and poor conservator, as good scientists and bad scientists. So some are good, some other are less good. And the less good usually are the most conservative, because they don't, they are not stupid, but they don't want to change the way of applying stuff. So that's, but this methodology, usually you use application methodology that are very close to their way of applying material and way of thinking. So that's sometimes with Italian conservators it's complicated. With some other country, maybe they are more open. It depends. It depends on and then it depends also on the institution. There's some institutions are more open, some are less open to innovation. So it's.
So that's interesting, because some of the students like studying culture heritage science here, so they might end up with being a scientist, or maybe a conservator, or someone working in the field of culture heritage. So no matter what kind of role you're gonna be open-minded. So okay, and then be open to collaborations. Okay. Any question from you? Yeah. Side.
Hello. There was a very nice demo video of how you use the gel to clean the painting. But I'm also kind of curious. I've been working with porcelain and pottery, especially ceramics that have been in the submerged underwater for many years. Have you heard of the Nanhai shipwreck?
Yeah.
Yeah, I'm also curious. So if we use this gel on, let's say, the porcelain or the pottery there, would it be able to clean or absorb the salts involved?
Yes, this gel absorbs salt, and you can use for absorbing, but Depending on the salt you want to remove, we can formulate specific gel that complex the salt to absorb much more. These are not specific for absorbing ion.
Yes, because I was also
the example that I show in the last with bronze, so this is a polyacrylic acid related gel, and then it can solubilize much better and complex with the carboxyl group specific ion. So it depends what you want to remove, but most of this gel absorbs salt. Anyway, by osmotic pressure. So these are gels that if you put over a surface that contains salt, by osmotic pressure, this salt is diffused into the gel, because this is what the physics tells to the salt. Then you can wash the gel and put back. It's a slow process, but we use in Leonardo da Vinci in Milan, the monochrome, to do this. So to remove salt from a wall, it was a wall painting, single color by Leonardo da Vinci. And we had to remove all the salt. So then depends on the salt. Some salt needs to be complexed. Some other doesn't matter. They just move by osmotic pressure.
All right. Additional question. As you know,
but then if you want to remove salt, you don't need the gel I show you here. You need gel with much larger thickness. So these gel usually are 1 millimeter, 2 millimeter thick, and are used for paintings because they're flexible and can adapt to the surface. You want to have a reservoir that pump the salt into the gel. So it's better if you use a thicker gel than this thinner, because otherwise you have to replace continuously. So it's boring.
So it'll need to be like submerged in the gel then, let's say.
Well, yeah, more or less. Yeah.
All right. Another quick question. So as some ceramics are rather porous, and well, considering we're cleaning out the salt, that would be okay. Would there be a problem if, let's say, we would need to observe some of the substances like still in the porous part of the ceramics? Would this gel also clean that out?
No, I couldn't catch the question. So the gel doesn't release anything. The gel cannot release any substance, can only absorb. It can release something if I mean, the materials that you want to release is contained into the gel. If you want to release on purpose, you can do that. But the neat gel cannot release anything. So you can just move the salt from the pore out of the pore. Then it depends on the pore size, because if the pore is a certain size, you have to formulate the gel in different way, because it depends. The osmotic pressure is not enough to remove something from a pore if the pore is too small, because you have capillarity and osmotic. So they fight each other in this case. So but we can formulate in a different way.
All right, makes sense. Thank you.
Welcome.
Okay. So any other questions? Okay. So no questions? Okay. So ladies and gentlemen, thank you very much for your participation in this forum. I hope that you enjoy this talk and this program. So thank you and have a great night. Okay. Maybe,